Okay, I think we can start. Before starting, a quick announcement. So Thursday, 2 days from now, in the afternoon, as we have already said, there will be on top of the hill in the old villa of Galileo, the award of the Galilei medal. So there will be a few seminars, a few presentations, and also a small apero, I think, at the end. If anybody wants to join, since the space in the villa of Galileo is limited, put your name or put a cross next to your name on this list here. I leave it on the desk. So we have a rough counting of how many people want to attend. And then we're trying to understand how we go. We can either make a wall call together uphill, or maybe there is an issue with the road being closed in case we are trying to organize a transportation, but we will tell you. No, we don't. No, anyway, the important information, if you want to come, put a cross next to your name here. Now, Alfredo Glioti will tell us about Flavour at the Muon Collider.
And other things.
And other things.
So yeah, this talk is based on a few papers. One of them is this one from 2022. And two more hopefully will come out soon. One should be really soon, the other one when the stars align, I don't know. So I will start with a plot that Patrick already showed the first day about the different way in which you can probe new physics. There's the energy direction, so you pump your collider energy hoping to create some new particles and observe them. Otherwise, you can go the precision route, so you try to increase your, for example, your luminosity, or you build some machine that is capable to test the standard model at a really precise level. And as Patrick already said the first day, the Muon Collider is a machine that would be capable of doing both things at the same time. And in particular, in this talk, I will talk about what I call the high energy probes. So the idea behind high energy probe is to start with the standard model thought as an effective field theory. So you have the normal standard model plus some correction that come from heavy new physics. And this correction come in form of some operators of higher dimension. For example, the leading terms are the dimension 6 operators. And when you try to compute amplitudes using these operators here, you realize that they give contribution that grow with the energy. So for the amplitude for a given process, we'll have some standard model contribution plus some contribution from these dimension 6 operators that is scaling with the energy as follows. It generally is energy squared over the new physics scale lambda squared. So what this tells you immediately is that the higher you can pump your energy of your machine, the higher scale you can reach with your experiment. Just to give you some more concrete numbers about this, suppose that you have some observable that receive some contribution from some beyond the standard model physics. And as I was saying before, the ratio between this BSM contribution over the standard model prediction scales roughly as E squared over lambda squared. And if you assume that you are able to measure something at the percent level precision at a 10 TeV machine, then you can see that you can probe new physics up to 100 TeV scale. Now, this is true for those processes that interfere with the standard model, but not all processes do. For example, flavor violating processes don't interfere in general with the standard model, reason being that they're extremely suppressed or even forbidden in the standard model. So in this case, you have energy scaling that goes with the 4th power of energy over this new physics scale. So it's a bit of a worse scaling with the energy. However, the standard model background is usually smaller. Now here I've written it in a schematic way, but usually this background comes from, let's say, your uncertainty in the flavor tagging of your final states. So you have a slower growth with the energy, but a smaller standard model background. So still, if you put in the numbers, you can see that even in this case, with no interference, you still can reach 100 TVs. And I will show you explicitly some results towards the end. Now, there is some big... But it's... No, but I still think it's a coincidence that the two things are more or less 100 TV. It's not a coincidence? Okay. No, for sure there's a small dependence with the dependence on this epsilon is small, I remember this. Yeah. Yeah. No, okay, but the 1.8 is for this one. There's no 1.8 on the in general for non-flavor. Okay, okay, whatever. Anyways, so there is some caveat to this argument I was talking about, and the reason being that if you want to probe new physics at the percent level, you also need some theoretical prediction that are accurate at the percent level. And this is complicated at the muon collider, especially when you consider some next to leading order effects in electroweak. For example, the exchange or the radiation of soft and collinear electroweak boson is especially enhanced at high energy. And in particular, these effects grow with these famous Sudakov double logs that are of this form here. So there is basically the squared log of the energy of the scattering over the weak scale. If you put in the numbers in the formula, you see that basically you get for a 10 TeV machine something that is 25%, and then this 25% is multiplied by some number that come from group theory, and so this can easily exceed 1, and so it can easily break perturbation theory. So what this is telling you is basically that if you want to make any meaningful prediction, you need to have control of these effects, and in particular, at least at the double log level, you need to be able to resum all these effects. So these Sudakovs here are special in the electroweak case as opposed to the usual QED and QCD ones. And the reason is that the electroweak symmetry is non-abelian and is also spontaneously broken. So the fact that it's non-abelian, it basically tells you that these Sudakov objects do not cancel out even in inclusive observables. Maybe you remember from QFT that in QED, these double logs always cancel out if you consider inclusive enough observables, but neither in QCD or electroweak, this is no longer true. And then, so the fact that the electroweak group is spontaneously broken tells you that basically the scattering state that you measure at your experiment are not singlets under the electroweak group. So concretely, you scatter muons, you don't scatter some muon neutrino object. Another interesting properties of this object is that the electroweak theory is weakly coupled, so you should be able to make predictions from clean theoretical prediction. There is an infrared cutoff that is given by the W mass, and this is a physical cutoff. And this is basically telling you that as opposed to QED, there is a notion in which you can define observables that are perfectly exclusive, and I will show you later, in the electroweak emission. This is not possible, of course, in QED and QCD. You always have to have some degree of inclusiveness, but for electroweak, this is not the case. And so the first part of the talk will be about how to handle these Sudakov objects and how to define some observables for which we know how to do this computation and this Sudakov resummation at various levels of inclusiveness. So I will focus on two observables that again are the ones for which we know how to do this computation. And we call them the exclusive and semi-inclusive observables. So the exclusive observable is basically a process in which you have the two initial muons, and then at the end you only have two final particles, and there is no electroweak radiation present at the end. Of course, you have to be a little bit inclusive on soft photons and soft gluons because you always have to, but you veto any soft and collinear radiation that is coming from electroweak. On the other hand, the exact opposite observable is the semi-inclusive. In the semi-inclusive, you have a process in which, again, the two muon go into a bunch of particles, of which there's two of them that are hard, so they carry most of the energy of the process. And then there is a bunch of electroweak radiation that is allowed up to some hardness threshold that, again, it's dictated on how hard you want these two particles to be. The reason for this semi-inclusive in the name is just that the notion of fully inclusive observables was discussed in literature and usually is in the context of also summing over the electroweak index of both initial and final states. But since we want some definite electroweak colors at the end and also the beginning, this is semi-inclusive. Now, the way in which we handle these double logs is through an evolution equation. So there's this infrared evolution equation that was first defined in this paper 99 from here. And basically, the idea is the following. So at the beginning, you start by defining and introducing some infrared cutoff, this lambda object here. I don't know where to point. And this is an unphysical cutoff that will regulate, again, the emission of both virtual and real electroweak bosons. Then you can compute diagrammatically at the double log level this derivative here. So the way in which whatever observable you're interested in changes as you change this infrared cutoff. What this gives you is this gives you some object that we call the kernel, and it gives you an evolution equation. The boundary condition for this evolution equation is simply the condition that when you take this infrared cutoff to be exactly equal to the collision energy, there is no radiation, neither virtual or real, and so the prediction for your observable at this scale is equal to the tree-level prediction. Then you use this equation here, and you basically can do a running. You solve it from this lambda equals e squared level down to lambda equals mw squared, and this procedure of running resums all these double logs. Now, for exclusive observables, as I was saying, exclusive observables are the one in which you forbid any soft collinear radiation in the final state. So this means that the only contribution is coming from virtual correction to your amplitudes. And in particular, the way in which you can compute the kernel is to consider the exchange between external legs in all possible combination of electroweak bosons. When you do this, you get an evolution equation that looks like this. And in particular, the kernel is this object here. The important properties of this is that it is color diagonal. So what this means is that different amplitudes with different SU2 indices are not mixed between each other. And then the weight of the size of this kernel object depends on the electroweak quantum number of all the particles that are in the process. And in particular, it scales with the Casimir, the SU2 Casimir of all the initial and final state particles, and also the hypercharge. For semi-inclusive observables, instead, you have to compute a little bit of a more complicated object. You cannot do it at the amplitude level, but you have to do it at the what we call the density matrix level. The density matrix is basically the product between the amplitude and the amplitude star, but where you allow different SU2 indices between the amplitude and the amplitude star. So this alpha and alpha bar. Furthermore, you sum over all possible real radiation. So there's this integral on the phase space and the sum of all the possible real radiation electroweak bosons that are exchanged here. And this object here gives you this D alpha alpha bar. So this is a tensor in the electroweak space. And you can compute the evolution equation of this tensor here, again, similarly to before, by consider all the exchanges of electroweak boson, both between two legs of the amplitude, but also to consider this exchange that cross between M and M star that basically correspond to real radiation. And objects like this, you can show that do not contribute at the double log level. So you only care about exchanging this object between external legs. And in this case, the evolution equation that you get is a bit more complicated because now this kernel is a tensor. And so what this is telling you is basically that different amplitudes with different that come from different multiplets of SU2 mix among each other. This is so for both exclusive and semi-inclusive, you can solve this evolution equation analytically. And I've tried to sketch here simply the result. The result for the exclusive case is extremely simple, as I was saying before. You have that the exclusive cross-sections are basically proportional to the tree-level cross-section times an exponential suppression factor. I forgot to write here what is this L, but this L is basically this alpha times log squared. And basically, this is telling you that the more charge the external legs are under SU2, the more these the cross-section are suppressed compared to the tree-level prediction. And the intuitive way to understand this is basically that as you increase the energy, the particles want to radiate more and more electroweak bosons, so it's more and more unlikely to have a process in which you don't radiate anything. For the semi-inclusive, instead, as I was saying, you have this more complicated tensor that is made of two parts. You have a part that is basically the same as the exclusive case, and the second part instead is a mixing term between different processes in the same multiplet, and this guy is not suppressed and mixes almost order one all the possible processes. So here I have a plot, two plots that show the effects and the size of this double logs here for two cases. Now there's a lot of lines here. I will tell you which one are relevant and which one you can ignore. But so if you start from the blue lines, so on the plot on the left is about TT bar production, while the plot on the right is about production of W with transverse polarization. So if you look at the blue bar is basically the cross-section that you get if you include these double logs at fixed order, so at the first order. And you can see that already in the case of this production of WW, the correction from this next to leading order is basically 100% already at 4-5 TeV. So this is telling you that you have to resum these objects if you want to have any prediction at few TeV energy. And the result of this resummation is a red bar. You can see here and here. And now this object is, and yeah, what you can see is that there is a large suppression compared to the tree-level prediction. For example, again, in this WW case, at 10 TeV, the cross-section is 80% than what you would expect at tree-level. 20? Minus 80. What? It's 20%, yes, sorry. I got confused. Meaning it's suppressed. Then also in this plot, you can see what is the effect of single logs. So all the computation that we have done are valid at double log level. So you might wonder what happens when you go to the next order, so single logs. Now the single logs, we only did it on the virtual case and at fixed order because they were computed in this paper by Denner and Pozzorini. And it's the black line. So if you compare the red line and to the black line, you can see what is the effect of these single log objects. And you can see that it's, I think it's order 10-20% correction on top of the double log. However, this correction is also would also depend on the angle, so it would be something more complicated. For example, if the single log would dominate in the extremely forward and backward region. But since we don't know how to do this resummation for the single logs, we did it only at fixed order. Yes? So it would be the energy at which collision happens. So it's the square root of S. E plus E, I don't know, E plus E minus 2 TT bar, and the TT bar is an invariant mass of x-axis. Whatever is in the x-axis. So I don't know if you look at 10 TeV means that I am producing TT bar pair at 10 TeV invariant mass. No, this is the exclusive case, so there's no radiation. There's a bit of QED radiation, but around 10 TeV. Yes. So if you emit a W, it's you get this thing that is in the so you don't call it again is not, you don't put it in the exclusive observable bucket, but you would put it in the semi-inclusive observable, and it's basically this dashed line over here. So it's sorry, which no, this is with when the final state is only TT bar. So it could also be that you have produced two B, and then this B have radiated a W, and they became a T. So here I'm looking at this final state that is TT bar. So this TT bar will receive contribution also from the production of two hard BB bar that then radiate Ws and become TT bar. So in the exclusive, it's exclusive, but in this dashed line, the dashed line are the same inclusive, so they include this process. No. So if there's a B and a W, I call it a B. Assuming that the B is energetic enough. So the request is that you have, so in the final state, you would need to have two particles that are carrying basically almost all of the energy of your machine. So yeah, 80%. That was, yeah, 80%. I was writing it here, it's small. So if it carries 80% of the energy, I call it a hard particle, and so I put it in the, so if I see two tops that carry 80% of the energy, I call it a top final state.
If a B carries 80% of the energy, and there is a W which carries 20%.
I call it, yeah, but it will be in the same inclusive for the BB production.
Top radiates a W becomes a B.
Yeah, but what I'm interested in is the final state after all the radiation.
But why do we do that? I mean, naively I would expect that you do the analogous to, I don't know, 3D radiation. You have your two final state, your two particle final state, and then you add on top of the W radiation the B, so T bar B W final state, according to the phase, but not of the B of the top.
It's the same. Meta. If you, so if you do next to leading order computation, you either get the blue or the red, depending if you have both the double and single logs. If you have both, okay, you will get the green. Yeah. Plus, yes. Now this is for a specific angle, so the single logs again has an angle dependence. Now I don't remember which angle we chose here or if we integrated, but maybe we integrated. So this the relation between blue and green also has some angular dependence. But if
You have no way to distinguish. You're putting everything together, initial and final state.
yes, yeah, you need to sum over everything so that so that the no. Okay. So here I will tell you why this radiation is interesting also for studying BSM physics. As an example process, you can look at the production of E plus, E minus. So you have this one here is the exclusive observable. So you start from E plus, mu minus, and you produce an E plus, E minus, and that's it. Instead, this is the semi-inclusive case. So you start from mu plus, mu minus, and then there is some radiation, and in the end, you get E plus, E minus carrying most of the energy, plus some radiation. Now, the interesting part about this is that since this radiation is soft, the hard collision now happens between a muon and a neutrino, and going to an electron and a neutrino. So basically, you are probing some different scattering compared to what you would expect at tree level. So basically, the muon collider is also a neutrino collider. And another thing that happens is that you can have final state that are charged thanks to the emission of this W boson's case. So with the same probability, basically, as these ones here, you can have the production of an electron-neutrino pair in the final state. And again, this is sensitive to a different kind of hard scattering, that is this one here. And you can see the relation between all these objects in this plot here. This is in these WY parameters, but the green is the constraint that you will get using only the exclusive observable. The brown, red, whatever it is the contour that you would get from using the semi-inclusive only, and you can see that they are not aligned. And the reason is that the semi-inclusive also includes this kind of neutrino scattering events that have a different dependence on the new physics parameters. And even more striking is the charge final state that goes in a completely different direction because it's only sensitive to this W parameter. It's only sensitive on Y and it's insensitive. No, it's sensitive to W and it's sensitive to Y. And so it goes completely vertical in this plot. And so when you combine all three together, since they are three independent observable, you get a bound that each is much stronger than you would expect normally. Sorry, what? No, it's one exclusive. It's the top left. It's exclusive. This is semi-inclusive, and this is also semi-inclusive. But in principle, yes. But so in my definition, this W plus again is extremely soft. So it's yes. Yeah, I guess you could compute a 2 to 3 process in which all three have some energy and call it exclusive. Yes. I don't know. If you sorry, what? Mhm. No, you don't sum them, you combine them. So here I'm not summing the three things, I'm combining them as independent observables. Okay, then you sum them at the likelihood level, not at the cross. Okay. Well, complicated question because because I mean the prediction that your simulator will give you for this, it's order 1 wrong. Now for E plus E minus final state, maybe it's not order 1, but it's 50%. It's the it's the same as TT bar, I guess, because there's small dependence on the hypercharge, but they're still doublets. So I guess that if you do it at 10 TeV, it's the cross sections will be suppressed by roughly 50%. What quantitative? So the dependence on the hardest cut, you can include it as a single log correction. Because if you think about it, the double log of 80% energy squared, you can expand it as the double log of the full energy plus a single log correction. That is basically a log of the energy times the log of this 80% number. So it's basically so in the end, we consider these two objects to come out at the full energy of the collider, because the correction is basically something that enters at the next link order. So it's single log correction. Not sure how clear it was to expand it. But then when you do the summing with the logs of summing, this order, that's kind of like the beefy presentation. But then, so I'm trying to understand, as I change this 80% parameter, how do these two?
I think it's a bit like the jet for the energy threshold in thermal finder. That the threshold for the soft.
Yeah, I feel like you have pressure radiation.
Yeah, the threshold, the total energy radiation, but that's like the log of delta I. Here is the log of delta I already. And so if you make delta I already, so if you make 2, so if 80% becomes 99%, then you're sure that it's going to happen. So it's 80%, it's log of one thing. That's why 80%.
No, also, I don't know if it's related, but regarding the angular dependence, we are always considering this process to happen in a central region in angle, so that basically ST and U are all of the same order. Again, so that you can neglect the difference between ST and U, and so you can neglect this huge correction that would come from the difference of the three. So the discussion that before I was talking about combining these two. So where the final state is the same, E plus E minus and also E plus E minus.
That's exactly the BW that we are saying before. That's the same thing, no?
Yeah, but it's not including it as the. I mean, I'm putting them in the same plane because it depends on the same new physics parameter, but I don't. Yeah, but it's. No, it's a. There are 3 independent and different processes that you can measure, and they are independent. They're both independent. All 3 are independent. Now this plot is just putting three processes as an example. Then when you do your analysis, you put all the possible things together.
Then we would really see, okay, these are the final states.
There is an electron and there is.
You could also do plus and minus invisible and a number of doubles.
Yeah.
No, you can't,
Yep.
no, because here you assume that you can see the double because they are real particles. You distinguish between radiation and without radiation.
Well, more than. Sorry? No, that's also a possibility. It's just that you. No, we don't include it because it's difficult to. Yeah.
Sure. You can now, so again,
Oh, if you
Yeah,
have
missing.
one neutrino, you can.
where you went from the second level.
No, we include everything. So that's fine. That's simple because we include all possible 2-particle final states with and without radiation, excluding this neutrino-neutrino case because it's a bit pathological. No, we are inclusive. We are inclusive over the soft radiations. On the soft radiation, we are inclusive. These W's here, you are inclusive. You sum over all possible number of W and all possible number of Z and all possible of photons emission in all directions. No, but
on soft laptop. No, we are. Cioè, ora lidiare. Final state, the final state, don't touch the hard. The hard, the two, etc. It's not only the matter. The rest is not matter. So it could be soft laptops, whatever.
in principle, yes. Again, yeah, roughly, yeah. The total should be this famous 20%. The total summing all radiation, yes, should be this 2 TV of if you have a 10 TV machine. The total. But then this 20% just this 80% is an example. It's not a particularly meaningful number.
Recognize both can recognize both there. So you put no. But this pre-labeling science, it's still in my brain. Because I mean this space, I mean this part of the space of dipole. It's just as if you go into a kinematic configuration, you would say, okay,
yeah. Yes. Yes. Mm-hmm. No. No, we don't.
I guess they're putting it in the below diagram. Oh, there, yes. Plus and minus one. The third diagram, yes, is exactly there. No, but you don't distinguish only the final state. You should have all the possible variations. Sophia, no, but 80% of the energy to the electron is.
I mean, if the electron in the end are hard enough, yes, it's here. The final electron emit, well, I mean, if you still have electrons in the at the end of this emission, then yes. Mm-hmm. Yeah, it would be a no, but we didn't include those. Yeah, no, the no, we didn't include them. Final state, no, we don't have it. No, but I think that it is a double loop. No.
Question is, when I'm saying pure depth cross section versus what is the threshold summation cross section? If I have a jet depth, I can ask the question, what is the right cross section? But for the exclusive one, I guess without the definition, I don't know what cross section to do without the exclusive one. There is no exclusive. There is some soft variation for which you will need to use some sort of definition based photo, of course. Okay. So the question is not to be asked about the exclusive one, mostly to be asked about the other one. But there is a difference. I mean, where you see this probably most commonly would be this analog jet physics, like the sigma over d y times 3. So the 2 jet relation comes over the 3 jet. This is exactly the regime where you see somehow you get from the collinear, from the large log regime.
I suggest maybe.
You go on. Yeah, it's 4.
No, I mean, it's good. The spirit of GGI is to have these discussions, but maybe.
Anyway, it's mostly results from now. So basically what we did is study all these 2-to-2 processes. And so by all, I mean all di-Fermion and all di-boson processes at the exclusive, semi-inclusive, and also semi-inclusive with charge finite state level. This is basically a complete list, I think. And for all of these processes, we included in the calculation the contribution that grows with the energy coming from these dimension 6 operators. If you want, the results are available, and also the mathematical notebook that computes everything. It's in this GitHub here. And now I will show you the results, basically. If you remember, we started at the beginning, 1 hour ago, saying that the Muon Collider can probe 100 TeV physics. And this is basically partial, a part of the results of a global fit that we did that includes, again, all diboson, dilepton, and difermion production. And you can see that basically the Muon Collider, so these blue bars are all at the 100 TeV level. These first columns here are from diboson production, the rest are from dilepton production, and then there's a similar plot here for dicore production in all possible final state. Now, this plot here ignores Flavour. Flavour will come in a couple of slides. But yes, this is the single operator bound. This is the global. Sorry, the other way around. The stronger is the single operator. The weaker is the global fit. And in the global fit, there's also inclusion of all VBF process that I think that Shin will talk about Thursday morning. But they're not in this here. Now, just to be more concrete about these results translated into a more physical parameter space, we did these plots here that are basically the reach that you would expect at a 10 TeV Muon Collider for two example BSM models that are strongly coupled models, so composite X, that gets to a mass reach of roughly 50 GeV for exclusion. And for a weakly coupled model, this Z prime, you can get even higher depending on the value of the coupling, but it's also hundreds of TeV. So now moving to Flavour. Basically what we did is also another analysis in which we include also Flavour violating final state. Here I put some example. That's the famous BS mu mu. So starting from 2 muon and going and creating a BS pair. Or also electron Flavour violation, so 2 muons going into a muon and an electron. And also in this case, you can exploit the same energy growth as previously and to probe new physics. And I will show you that basically the new physics reach for at least for a specific kind, for this specific kind of processes is better in some places or comparable to dedicated low energy measurements. So basically the Muon Collider is also a Flavour machine. This plot here shows how the Muon Collider can give you a bunch of different observables that you can combine together to constrain new physics. So here I'm looking at these two operators here that are basically 2 muons and then a third generation quark and a second generation quark, triplet and singlet. And this parameter space is probed by many different final states. You have the production of a B and a jet. You have the production of top and a charm. And these two have a different dependence on these operators, and so you can combine them and get a smaller bound. And then you also have this charge final state I was talking about before, for example, T and a light jet or B-C pair. And again, you can combine everything. So basically, the Muon Collider gives you a bunch of different things that you can measure and that you can combine together. And this gives you a much stronger bound on BSM physics than what you would expect. And yeah, here is all the possible things you can combine, different flavor, different level of inclusiveness, and also this charge final state. So in this Flavour analysis, we included all possible Flavour final state. So the production of 2 quark that now we assume that you can Flavour tag up to some efficiencies. So 2 jet, 2 charm, 2 bottom, and all the combination. And then also the same for 2 lepton production. For this analysis, of course, it's crucial to have some estimate of what you can and what you cannot tag and at which probabilities. So we included everything. And yeah, I will show you now some results for a 3 TeV and a 10 TeV Muon Collider compared to what low energy experiment at the end of so current bounds and also at the end of ILUMI can probe. These results here are for B transitions. So this is what you what you have seen many times in, I guess, flavor transition. There's the, for example, the BS mu mu processes are in here. So the muon collider 10 TV is this red bar, the 3 TV is the orange, and the gray is the low energy. The field is the current bound, while the dashed is what is predicted to be at the end of ILUMI and Bell 2, I think, so in 20, 30 years. So in this case, the reach of the muon collider is comparable to what will be the reach of dedicated experiment, but this is not the case for other observables. For example, flavor violating top processes, you can see that the muon collider also reach hundreds of TV, and the bound coming from low energy is much below in this scale. I think it's TV level that comes from looking at some top decays, basically. And then similar plot also for lepton flavor violation. Here we have tau and 3 muons, 2 muons tau electron and 3 muons and an electron. And even in this case, you get to hundreds of TV of new physics reach compared to the, okay, this comparison not 100% fair because there's, if you're only interested in general in lepton flavor violation, you can probe it much better, for example, at mu2e or mu3 conversions. But for this specific four fermion contact interaction, this is the muon collider would offer the better probe. And yeah, this is a final plot that was also in the report of the muon collider. That is basically just a short version of the previous bars, comparing a few selected observables to the low energy measurement and also their prediction. And you can see how the muon collider compares with those. Okay, so just the conclusion. Yeah, question. Yeah, so for example, here the current reach is 50 and the future is 140. So this would be at the end of ILUMI and the Bell 2, and I don't remember if there's something else, but yeah. Anyway, conclusion really quick because it's late. Muon collider can probe new physics up to hundreds of TV, and you can, thanks to this radiation effect, you have a bunch of observables that you can combine together and explore new physics in a richer way than you would expect just from tree-level analysis. And this extends also to flavor violating observables. And yeah, also this study of electroweak radiation, even if you don't see any new physics at the muon collider, will be said, but even just understanding and studying a more complete picture of this electroweak radiation would be a great understanding of just pure normal quantum field theory. No, thank you. Yeah.
But that favorite part, you assume some favorite part is
Yes. So we have some estimates that now I don't remember by heart. If you have the draft over there, you can check it. But we have a bunch of, we have considered all possible tags and mistag probabilities. For example, from what I remember, the tau have a 50% probability of being correctly reconstructed as a tau or not, while for the quarks, we have some probability of getting reconstructed or getting mistagged as a different flavor. We took from, yeah. If you want the numbers, we can talk about them later, but.
So this reach on the flavor operators is single operator.
No, this one is just single operator.
Yeah, in this case, the emission of electroweak radiation is more tricky, and the fact that it has the impact that it has depends on your assumptions on how much you violate flavor in this higher dimension. Take TT bar, take TT bar like a half scattering, let's say TT bar TE, and then you emit a W from the top.
Okay.
And then you have a small probability with CKM matrix element that this W is emitted together with a string instead of a bottom. And
So
then
this,
will have contributed with a
no, I think this one we include them, the flavor, yeah, okay.
But depends on, well, if your TB scattering is the same size as the flavor violating one, then clearly this emission is irrelevant.
Mhm.
Instead, if you're in a situation where your operator is already flavor suppressed, if you look at, for instance, a hard BS scattering, then the emission of a soft W from the third generation operator becomes of the same order as the
In partially, maybe if you write it's better, but I think that we include these things.
Yeah, but
I
as you
think
said
with-
before, no? In the
yeah.
case of the electron, you have different operators, hard scatterings,
Yep.
enter in the same final state. Because
Yes.
they're mixed by the emission.
Ah, you mean that a global fit would be interesting?
Well,
That's what.
Fine. How big the different operators are when they enter in the observable that are defining. This depends on your flavor assumption.
Yep.
Yes. If you do single operator, then you get a very different result when you assume that the flavor blind is much bigger than the flavor violating, or if you assume that there are, let's say, not.
No, yeah, we didn't do an.
Global fit can be, but it, yeah, the global fluidity may deteriorate a lot, sure. Yeah.
But not only the global, also the single operator. Because if your cross section has a contribution from two different operators, one which is TT bar and the other which is a flavor violating thing, right? Now, if the two operators have the same coefficient, then one of the two is irrelevant because the emission of a W is CKM suppressed. Instead, if the one without emission of a W is also suppressed because of your flavor assumption, then you get a very different result.
The combined fit is negative, but you have to put both. Yeah.
We didn't do a global fit with this flavor.
But this means that most of these error bars are given by without radiation. Without radiation, you agree?
There are combination of factors.
Well, for single operator reach, the with and without radiation don't help too much.
Exactly.
No,
Yeah.
it will be the same. Yeah. I mean, fit in the sense that one of them goes down and the fit of the other goes up.
Yeah, but this yes, tutto. What? So you compute BD production, so mu going to a B and a D. You tutto, yes. Then you combine all the exclusive, inclusive, all the mistag probability. I don't know. Yes. BS, no, but BS is included, sorry. BB, but mistagged as a, yes, yeah, in the same way as before, yeah.
We get the same as part.
I guess you can see it from here. If you do the single operator, I don't know, including these two, you get, I don't know, this line here. If you include also this same inclusive and also a couple more that are not drawn here, the contour shrinks a bit, but the the contour shrinks a lot, but the single operators are basically the same.
But exactly here, you see how
Yeah.
you combine these different things, it
Mhm.
can change.